Okay, thank you so much. So first of all, I thank the organizers. It's very good to be here. I got my first full night of sleep last night since the last 4 months, so it's a real treat. Thank you. And well, I'm happy to discuss all the science here. I also very grateful for Jacopo, who did a very nice introduction about the field in the first lecture. And well, he mentioned actually that photons that are confined inside the cavity, and they can behave like a fluid of light, okay? And he mentioned that, such photons can behave like water or air. And here, what I'm going to show you is that actually photons confined in lattices of a microcavity can behave as electrons in actually crystalline matter, and in particular, I'll be interested in 2D crystals, okay? So let me start with some example of real-life 2D crystals, because this is where we actually find our inspiration. So one of the most famous 2D crystal is graphene. It's an array of carbon atoms, okay, that form a honeycomb lattice on this type, and in fact, there is these days a whole zoo of such materials, including hexagonal boron nitride or van der Waals materials, TMDs, that are very interesting also for the optical point of view for the opticians here. They have some nice optical response and a lot of nice science is done there. Most of the properties of these materials can be related to their band dispersion. Okay, so due to the hybridation of all these atoms and their coupling together, they form energy bands. So for instance, for a graphene lattice, you have 2 atoms per unit cell, so you will end up with 2 energy bands. They plot here the energies as a function of the wave vectors. And for instance, many of the very interesting properties of graphene are related to the fact that here, at this point in the Brillouin zone, the band touch. Graphene is a semi-metal, okay? And due to this band touching point and the linear dispersion, they have lots of properties of graphene here. But this is like a completely single particle physics, okay, or linear physics. Now you need to remember that electrons also, they interact together. So if you take into account electron-electron interactions, many body effects can appear. I provide an example here from 2018 where some people at MIT took actually 2 sheets of graphene, okay, on top of each other, so the electrons interact, and then they change a little bit the angle between the 2 layers, and at some angle called the magic angle, due to the strong correlations between the electrons, they realized that this bilayer material could become a superconductor, okay? And in such material, fractional quantum states also has been observed, so many body physics can be also due to this electron-electron interactions. So the question that I want to ask is, well, how can you make photons behave like electrons in a 2D crystals? And I will decline it in 2 sub-questions. The first one, I will try to explain to you how we engineer band structures for photons in some microcavity materials. And then, well, if I have some time, I will see how I manage with time. I would like to discuss how to make the photons interact in these materials and what kind of nonlinear effects we can engineer and observe in these systems. So as Jacopo already mentioned, this is the answer to this question in principle is not that trivial, okay? Because first of all, if you consider photons in vacuum, well, they have a very simple dispersion relation. It's a linear dispersion relation, okay? So this is, basically the photons have no mass, and so it's going to be very difficult to make, to engineer these dispersions. Second of all, they interact very weakly. They have no charge, okay? So it's a very different system from these electronic 2D materials that I just mentioned. The third point also is that photons are bosons, contrary to electrons, which are fermions. But this, I will already eliminate this question, saying that, okay, we are not going to be interested exactly in the physics of the fermionic systems that I was mentioning earlier, but we are going to be interested in bosonic equivalence of these effects. So we are going to be interested in bosonic matter. One example of a very famous Hamiltonian for bosonic systems is, for instance, the Bose-Hugbart model here that describes particles that hop on lattice sites with some on-site interactions. Okay, so this is typically the kind of system we'll be interested in. So why do we want to do photonic matter? So first of all, by studying this system optically, this kind of photonic system, we can address fundamental questions related to the physics of interacting particle on a lattice. And we have new ways to probe it, basically using all the tools of optics and quantum optics. And also, as Jakob also mentioned a bit earlier, we can use some of these concepts actually to design some new types of photonic devices, like waveguides, insulator, and so on. Okay, so the question is, well, can we realize 2D arrays of 2D arrays using light? And one of the answer is yes, and I'm citing here a series of articles that got published around 2006 and 2007 that gave one possible avenue to implement such things. And so what they said is, well, if you take cavity photons, so you take photons, you confine them into a cavity that are coupled to a nonlinear medium. So here the nonlinear medium is this kind of two-level system, okay, in this cartoon picture here. Then the photons will behave as massive and interacting particles. So this is what Jacopo already explained in the previous talk. And now, if you take an array of such cavity and you couple them together, you have this hopping term here. It's like the hopping term in the Bose-Hugbart Hamiltonian. You can actually implement a synthetic material, or in the limit where the interactions are strong enough, a synthetic quantum material. Okay. So this was really discussed in this original paper. Where, well, for instance, if you look at the titles, you can understand like quantum phase transition of light, strongly interacting polaritons in coupled arrays of cavities. So it's really where this idea was introduced. Okay, so I'm going to discuss some of the work that we do at the Center for Nanoscience and Nanotechnologies. This is in Palaiseau on the Paris-Saclay campus. This is a work that we lead together with Jacqueline Bloch at C2N, and I'm going to discuss mostly of some work that has been realized by Martin Guillot here, former PhD student in the group, and Cédric Blanchard, who is currently a PhD student in the group. All right, so let me start by discussing the band structure engineering in semiconductor lattices. Okay. So the system, our system of choice is actually made of semiconductor materials. Okay, these semiconductor materials, they are grown by molecular beam epitaxy. It's a technique where you can grow crystals atomic layer by atomic layer in a very controlled fashion, so that you can actually fabricate stacks of different semiconductor materials. So typically here, each gray level represents a different material. It's going to be, for instance, gallium arsenide or aluminum arsenide layers. These materials have actually optically, they have different indices of refraction. So due to this index of refraction mismatch, you can organize some interference effect at each interface. And in fact, if you realize what is called the Bragg condition, which is that each layer has to be in optical thickness lambda over 4, a quarter of the wavelength, you will actually fabricate a very, very good mirror. Okay, it's an interference, a mirror type based on interference with 99.999% reflectivity. And now if you place two of such mirrors with a small spacer in the middle, which is also typically made of some semiconductor material, you actually define a cavity where the photons are going to be confined. Okay, so the photons, they bounce back and forth inside the cavity. They stay for some time, which is the lifetime of the photon, and then they escape. And as we saw in the first lecture, we can actually write the energy of the photon in the cavity as such. So it's h bar c over n times k as usual, but here the k z, the z component of the the wave vector is quantized due to the waveguide condition in the cavity. And so if you Taylor expand this expression around k equals 0, you can notice that the dispersion of the cavity will be typically parabolic, like this, the dispersion of the photon in the cavity. And so this is typically the dispersion of a massive particle, and so this is why, as we saw earlier, the photon in the cavity can behave as a massive particle, okay? So this is the first ingredient that we will use to then fabricate our synthetic materials. Then, what I said earlier is that these crystals are fabricated by molecular beam epitaxy. So when they come out of the machine, typically they are like a big wafer, typically 5 centimeters in diameter. It's really a 2D type of cavity. And then we can use some nanotechnology techniques like etching, e-beam lithography etching, to define some small microstructures. So our building block is actually going to be a micropillar. Okay, it's a small cylinder, typically a few microns in diameter, where the light is going to be confined not only in the z direction, but in fact, you see this is typically the dimension of the wavelength of the light that propagates in the medium. So it's in fact confined in all directions. It's confined in 3D. So how do we probe these cavities? So we do optics. Typically, we place them in a cryostat. It is cooled down at 4 Kelvin. And we excite it with a laser beam that is focused onto the entrance surface of the sample. And then we collect the light that is transmitted through the cavity, and we image it on the system, a spectrometer and camera, for instance. So if we do this experiment on a single site, a single micropillar, and we record the energy here versus the position. So we do a real space image on the spectrometer and we disperse it. So we have energy vertically and position here. We get the spectrum and we see that we have actually discrete energy levels, and these discrete energy levels are a direct consequence of the fact that the light is confined in all directions, okay? And so these are actually what we are going to call our photonic orbitals, okay? So the micropillar, if you want, you can see it as an artificial atom, a photonic atom that we'll then use to fabricate larger lattices, okay? And the lowest energy state here is the fundamental state of the structure, has the symmetry that we call S. It's like a S orbital, okay, for the atom. And you look, for instance, at the next orbital, you see that it has 2 lobes like this with the 0 in the middle, and it resembles the p orbital of hydrogen atom, for example. Okay. Well, now with this kind of nano fabrication technique, we have a very good resolution down to the nanometer. Okay, so we can define any kind of structures. I focus for the moment on one single atom. Now, if we fabricate 2 coupled cavities like this, okay, it's a dimer. If you want a dimer, a photonic molecule, the photon will be able to hop actually from one cavity to the next because of some evanescent coupling between both of them. Okay, so the electric field can leak a little bit from one cavity to the next, and this acts as a coupling between the 2 sides. So if I do again this measurement of the spectrum versus position, I see that now these levels hybridize together due to the coupling, and we have here, for instance, due to the hybridization of the 2 S modes of the 2 sides, we have 2 levels now, which are the bonding orbital of my photonic molecule and the anti-bonding orbital of this photonic molecule with a 0 here in the middle. Same thing for the higher p states, okay? So I can scale up the approach and, for instance, fabricate a 1D lattice, okay, of coupled pillars, perform again the same experiment, and due now to the coupling between all the neighboring sites like this, what we see is that energy bands are going to appear. So this is again a spectrum. You see all these orbitals hybridize together, and we have a band, energy band, as a function here of position. Okay. So this is one way to probe the system. The other way to probe the system is just to modify a little bit the setup that I described earlier. Okay, we excite it optically still, we collect the photons. But if you remember earlier, I was just making an image of the back surface onto the spectrometer using 2 lenses, a telescope. Here I'm going to add an extra lens in the middle. And this extra lens in the middle is going to do a Fourier transform, okay, an analog Fourier transform. And it's basically going to convert the angle of the light that escapes the cavity into a position. So we do Fourier space imaging, and so on the entrance slit of the spectrometer, we have an image of the K-space distribution of the photons. We have direct mapping of angle to position. We send it into a spectrometer so we can disperse and have directly an image of the energy versus the wave vector. So this is exactly the dispersion relation of the material. Okay, so if I do that for the 1D lattice, this is the real space imaging technique where we see the energy bands versus position. Now I do the Fourier transform optically, and you get the energy bands here with a nice dispersions for the S bands and then for the P bands and so on. Okay, so this is how we are going to engineer bands and measure the band structure for these lattices. Okay, so now we can go all the way to 2D. Okay, so I showed you 1D lattices. Let's look into honeycomb lattices. We can basically fabricate these kind of structures where the pillars are etched in the form of this honeycomb lattice. It's a little bit special honeycomb lattice. This one, if you look, I circled some of the sites in green, some of the sites in red. It's just because they have slightly different sizes, okay? If you look, this one are a bit bigger, this one a bit smaller. So this actually introduces an on-site energy difference between both sites, because a small pillar means higher confinement energy, and so bigger energy on these sites. Okay, so it's called a staggered honeycomb lattice. The tight binding Hamiltonian writes like this: you have the on-site energy difference between the A site and the B site, and then you have the coupling between sites. Okay, so this typically implements HBN lattice, okay, hexagonal boron nitride material, but with photons. So one kind, I mean, this is a simple Hamiltonian. It's a lattice with 2 atoms per unit cell. So you can do the Fourier transform and write the block Hamiltonian in a reciprocal space. It's a 2x2 matrix, okay, where you see the on-site energy difference here, and then the coupling terms. So it's possible to diagonalize this matrix easily, and then to plot the energy as a function of K. And you end up with this kind of band structure. So you have 2 bands, because 2 atoms per unit cell, a bit like graphene here. These bands are gapped because of this energy difference, and the minimal spacing between the bands is twice the on-site energy difference. Okay, so this is typically the kind of band structure we expect for this type of materials. And we can apply these measurement techniques that I was describing earlier, and we obtain this kind of band distribution. So you recognize indeed the 2 bands, the lower energy band here, the upper energy band, and these 2 bands are gapped as expected for this type of HBN photonic lattice. Okay. Actually, this is one cut of the dispersion, okay, that we do by doing an image on the slit of the spectrometer. Then we can scan and do multiple cuts. And if we do multiple cuts, then we can completely measure the full band dispersion across the full K-space. And it looks like that. Okay, so this is this engineering of photonic lattice and how we manage to realize band structures for photons in semiconductor lattices. How do we do this full reconstruction? So, yeah?
No, I just try to get the geometry of the measurement.
So the measurement is still this one. So you have an image of the K-space at the entrance slit of your spectrometer, and then you select a cut with your slit, you disperse, and then you scan a lens in front of your spectrometer. And for each position of the lens, you get a different cuts. So for instance, you have a fixed KY, and you scan KZ. Okay. No? I see. Fine, I'll show you later. Okay, so let me switch to the second part. So I'm going to now spend a bit of time on this lattice that I just described, this Polariton HBN lattice. And I will discuss a recent experiment that we did to actually reconstruct experimental the full block Hamiltonian of the system, which means we are not only going to look at the eigen values of this Hamiltonian, but also we are going to measure the eigenvectors. Okay, so that's the trick I want to discuss here. So some motivations quickly. As you saw in the previous section, we discussed mostly the measurement of the dispersion. So it's the energies versus K. So we have basically been characterizing thoroughly the eigenenergies of this block Hamiltonian. What about the eigenvectors? So it turns out, as we saw in Jacopo's lecture, that sometimes the eigenvectors are needed to evaluate some physical quantities that are relevant to the system. So it's typical, for instance, in the field of topological physics, where, for instance, the Berry curvature for a given band is expressed as this. So it's a scalar product of the derivative of the different block wave functions of your Hamiltonian. Okay, so if you want really to measure that experimentally, to characterize these quantities experimentally, you need to know the eigenvectors. So that was the motivation here. How do we measure these eigenvectors? So this block Hamiltonian is a 2x2 matrix. Okay, so the eigenstates, they are going to be vectors of size 2, and they can be parameterized typically on a sphere, on a point carré sphere, by two angles. The phi angle, which is the azimuthal angle, and the theta angle, which is the polar angle. Okay. So basically, the system or the eigenvectors can be parameterized as a pseudospin. In our case, what pseudospin? It's the sublattice pseudospin. Okay, because this dimension here represents. We have two side per unit cell, so sites A, sublattice A, or sites B, sublattice B. Okay. So my Poincare sphere is the following. I consider that at the top, at the north pole, we have a state that is fully localized on one of the sublattice. Okay, so there is intensity only on one side out of two. When we are at the bottom, it's the other sublattice. And when we are at the equator, both sublattices are equally populated, okay, with a relative phase that is given by phi. That's what it means. And our goal is to measure this pseudospin, okay, on the Poincare sphere. So I just want to start with a small reminder here, because it's very similar to what you do when you want to measure the polarization state of light. Okay, if you have a light and you want to measure the polarization, usually what you do is you do a polarimetry experiment. So you send your light into a series of retarders and polarizers, so typically a quarter wave plate and a polarizer, and you can express the intensity of the light that goes through this system as a sum of different components. Each components are called the Stokes components, and they represent basically the coordinate of your state onto the Poincare sphere. And so by doing 4 measurements, you have 2 angles to characterize, this angle theta and phi. By doing 4 different measurements, intensity measurement, you have 4 equations. You can recover these 4 parameters that characterize fully your state. Okay. So we want to generalize this approach. Our pseudospin is not a polarization pseudospin, it's a sublattice pseudospin, but we want to generalize it to the case of photonic lattice. Okay, so I will go back to this dispersion measurement here, okay, where we have the energies as a function of K. And what I want to argue here in the next couple of minutes is that one thing I have not discussed so far is the intensity distribution. Okay, if you look at this picture, it's very obvious that there are some states that are quite bright, and there are some states that are very dark, in fact. And so what I want to explain now is that, in fact, looking at this intensity gives you some information about the underlying eigenstate. So let me give you a simple example. If you are at the center of the Brillouin zone here, it's the gamma point, so the lowest band contains the lowest energy state, and usually in the lattice, the lowest energy state is called the bonding state. It means like all sides, they oscillate in phase. They have the same phase, and so that gives you the lowest energy state. Since they have all the same phase, the light that propagates outside of the sample is going to interfere constructively, and so you have a bright state here, a lot of intensity. On the other hand, when you are at the top of the the high energy band, you have the anti-bonding states, which means that two neighboring sites, they are going to oscillate out of phase. And because of this out of phase condition, actually when you collect all the fields together, they interfere onto your detector, you will get destructive interference condition, and you have a dark state, okay? You have a bit of a subradiant state here. So to measure this state, we are going to use this interference condition in the dispersion measurement, and we are going to make 4 measurements, and it's like a polarimeter. We need to make 4 measurements, 4 intensity measurements. And to do these 4 measurements, what we do is we introduce in the setup I described earlier, where we image the lattice onto the spectrometer with 3 different lenses, we add a spatial light modulator in between polarizer and analyzer that is going to allow you to modify slightly the phases between the two sublattices. Okay, so we are going to do a real space image of the lattice onto a spatial light modulator, and we are going to say, okay, selectively, I'm going to introduce a given phase onto one sublattice with respect to the other. It's exactly what a quarter wave plate would do for a polarization state of light, but here we do it for the sublattice polarization. So let me give you an example here. So this is the typical dispersion measurement that I showed so far with the interference conditions that I described. And now we are going to introduce selectively a pi/2 phase shift for all sides of the B lattice, and we are going to reproduce this measurement. And what we obtain here, very obvious, is that, well, once we look at this new dispersion measurement, we have completely modified the interference condition onto the detector. So we don't have this destructive interference here, and so on. And now we do 4 different measurements. So a third measurement where we hide completely, we suppress the emission from one of the sublattice A, and then a 4th measurement where we completely suppress the emission from the other sublattice, and we only look at the band dispersion that comes from the superposition of the waves of this A sublattice. And we have our 4 measurements. And now we can do, typically, these linear combinations of these 4 measurements to go and recover at each K in the Brillouin zone the different Stokes parameters that characterize the position of this state onto the Poincaré sphere. Yes, indeed, because the SLM is between polarizer and analyzer. So you can project and for instance, completely extinguish one side or the other. Okay, so once we have these 4 measurements, we can, for each K, determine basically the coordinates of the corresponding block state onto the Poincaré sphere. And then we can reconstruct a map of this angle theta here that represents the polar angle of the state, and this angle phi as a function of kx and ky, okay, over the full Brillouin zone. So we can discuss a little bit what we observe here. If I look, for instance, at the center of the Brillouin zone, I see that theta is equal to 0. So we are on the equator of that sphere, meaning that there is equal intensity on both sublattices, A and B. And if I look at the azimuthal angle, it is 0, meaning that they have same phase. Okay, so we have 2 sublattices with same amplitude and same phase. So this corresponds to the bounding state that I was indeed describing at the beginning. What is interesting is that if you look here at the K and K prime point in the Brillouin zone, this special point here, this hexagon, you see that the theta, the polar angle, almost goes to 0, which means that we are completely localized on one of the sublattices and not on the other one. And this actually leads to the emergence of vortices in the phi map here, because basically phi is undefined at these points. Okay. And this leads to the emergence of singularity, for instance, when you calculate the Berry curvature, as we saw earlier in the talk of Jacopo for HBN, we have non-zero Berry curvatures at this point. Okay, so we have measured both the eigenvectors and the eigenvalues for this lattice. So in fact, what we can do is we can completely reconstruct the Hamiltonian, the block Hamiltonian for the system. So a convenient way to plot it is actually to decompose this Hamiltonian onto the basis of Pauli matrices. Okay, so we have the 4 Pauli matrices with 4 components in front of this matrix. And what I'm doing here is I am plotting these 4 real components. Okay, so this is lambda 0, the coefficient in front of identity, lambda 1 in front of the sigma 1 Pauli matrix, lambda 2 in front of the sigma 2, and so on. One interesting thing to discuss, for instance, is that if you look at, let me check which component I wanted to discuss here. At this component, the lambda 0 here, in principle, you expect it to be completely 0, as since I brought the Hamiltonian like this. Okay, there is no component with respect to the identity. This is just a component with respect to sigma 3. And it turns out that we see some non-zero components, and actually we were able to identify that because of some coupling to higher order modes in the block Hamiltonian, we need to introduce another term which corresponds basically to an effective next nearest neighbor coupling. Okay, so basically by reconstructing completely this Hamiltonian, we can fit precisely and we have a knob to really engineer precisely the Hamiltonian of our system. Okay, so we have measured the Hamiltonian of the system, and this allows us then to reconstruct some of these physical quantities I was mentioning earlier, which require the knowledge of this eigenvector. So typically, for instance, this is a reconstruction of the Berry curvature for this lattice, and we see that we have non-zero components of the Berry curvature around the k-values of the lattice. If we integrate over a full Brillouin zone, we see that these 2 components are going to cancel out. Okay, one is positive, one is negative. This is because this HBN is actually a trivial insulator from the point of view of topology. Okay, so the Chern number is 0. Nevertheless, this technique can be generalized to more bands, system with more bands, and we are working on that at the moment. In particular, when you add a polarization degree of freedom in the lattice, this can act as a spin-orbit coupling, and then you can actually realize Polariton topological insulators. And so our goal is to use now this technique to characterize such phases, especially near topological gaps. Okay. Good. So let me go to the next topic, which is related to interactions. Okay, how can we make photons interact? So far, we have seen how we engineer lattices, and whatever I discussed was single particle physics. We are looking at the dispersion as a function of k. As I mentioned earlier, if you want to realize this synthetic materials, there are 2 ingredients that are necessary, not only the coupling J here to realize band structure, but also you need to add some nonlinearity in your medium to be able to engineer interactions, effective interactions for the photons. So how do we do that? Well, in fact, when I was describing our samples earlier, I did not mention one thing, which is at the middle of the cavity, we actually place an active material. Okay, so this is done during the fabrication. In the cavity, we grow a semiconductor quantum well. Okay, so the semiconductor quantum well is a layer of different semiconductors, which have here different, not only optical property, but also electronic properties, so different band gaps. And at the center of the cavity, we have this few nanometer quantum well that can trap the charge carrier, so electrons and hole. And electrons and hole, they can form via Coulombic interaction a bound state, which is called the exciton, and that can be addressed optically. Okay, so typically in the near infrared, we can excite these excitons in the systems, and the excitons, they are composed of electrons and holes, so they are described by these bosonic operators here. The first one is simply the dispersion. These are massive particles, okay, in the semiconductor. So it's a parabolic dispersion times the number of excitons. And then these excitons are matter particles. They interact together. And so typically we have this kind of Coulombic interactions between the excitons. Now the sample is designed in such a way that when a photon enters the cavity, it can be absorbed in this active material. Okay, so we excite excitons. They have a certain lifetime, then they can re-emit a photon in the cavity and being reabsorbed like this multiple times, multiple Rabi cycles in the system. So in total, the total Hamiltonian for a system is the following. We have the photon number, exciton number. We have a Rabi coupling, okay, between exciton and photon that describes the process I was just mentioning. And then we have these exciton-exciton interactions, okay. So if we measured the dispersion for this planar type of sample, we obtain 2 bands here. So we have this kind of parabolic dispersion here, and we have an avoided crossing. And the avoided crossing is due to the coupling to the exciton. Okay, so the exciton here is at this energy. It is also a massive particle with a parabolic dispersion, but it is extremely flat because the exciton is 10 to the 5 heavier than the photon. Okay, and we observe this avoiding crossing here, very nicely resolved avoided crossing, which means that we are working in the strong coupling regime of cavity QED. And so at these points, we have states that are mixed states, okay, that are half light, half matter states that we call polaritons, okay? And because these polaritons, they spend, if you want, half of the time as a photon, half of the time of exciton, they interact together. And so that's how we can engineer polariton-polariton interactions, okay? So the nonlinear medium that we use in our system is a quantum well, and we engineer this way, typically going into the mean field regime, some Kerr nonlinearity, and we obtain this driven dissipative Gross-Pitayevsky equation that we discussed in the first lecture. Okay, so that is the nonlinear term. So what can we do with this type of nonlinearity? I'm going to come back to the single site example, where we have a single microcavity, okay? And we are going to scan it, scan a laser through the cavity and record the intensity as a function of the energy of the laser. When the power is really small, and this is normalized, we are in the linear regime, and we end up with a kind of a Lorentzian function here, which is the natural line width of the cavity. And when we increase the power, due to this nonlinear term here, what we see is that this Lorentzian gets distorted and actually shifted here, shifted to the blue to slightly higher energies. And this is because typically the interactions between polaritons are repulsive. Okay, so we have this Kerr energy shift as we increase the power, which shows that we can use the nonlinearities to be able to tune locally the energies in a lattice. Okay. One typical signature also of this kind of nonlinear response is the following. If now I place a laser and I try to excite the system slightly blue detuned from the energy state of the pillar here, initially I'm going to inject it very badly. I'm really injecting in the tails of the Lorentzian, if you want. So it's going, the power in the output is increasing slowly, and still this state is shifting towards the blue due to the repulsive interaction. And at some point it's going to cross the pump. And at the moment where it crosses the pump, then there is a huge jump because we can populate very efficiently the state. And we have this nonlinear jump. Okay, so typical nonlinear response for this kind of system, the Kerr nonlinear system. So what happens now if I scale up the system? So I consider first the dimer case. Okay, so in the dimer case, we have a bonding state and we have an anti-bonding state. So for the bonding state, two sides, they have the same phase, they oscillate in phase, whereas for the anti-bonding state, they are opposite in phase. Okay, they are very opposite in phase. We can excite each of the sites individually by focusing a laser on each of the sites. And what we are going to discuss here is an experiment where the energy of the laser is tuned to this anti-bonding state here, and the pumps, they respect the symmetry of the underlying state in the sense that we are going to induce a pi phase shift between both pumps. Okay. So when we start increasing the power, we have this repulsive, the blue shift of the states that is going to happen, okay, due to the repulsive interaction, and we are coupling very well to the states, so they shift, all fine. And then at some point, as we discussed for the one pillar example, this state here, which is lower in energy than the pump, is going to come into resonance with the pump, okay? And at that point, there is going to be a phase frustration because we are pumping with two pumps with opposite phases, but the state that reaches resonance has this symmetry. Both sides are oscillating in phase. And we ask the question, okay, what happens in that case? This is when the system is highly frustrated like this in the nonlinear region. So to look into that, we fabricating a chains of dimer, actually, not just a single dimer, but a full chain of dimers. So as you see here on this SEM image, you can see that each pillar are coupled together, but for some of them, the distance, the interdistance pillar is smaller than for the next ones. And so here you have small distance, large distance, small distance, large distance again. And this modulates the coupling, okay? So we have some strong coupling and some weak couplings. And so this realizes these chains of dimer. If you imagine what happens, you have two sites per unit cell here. So you will have two bands, two energy bands for the system. The two bands, they have the amplitude that is given by J prime, the weak coupling, and they are split in energy here by 2J, the strong coupling, okay? So if J prime is different from J, actually these two bands are gapped. The lowest energy band carries the bonding symmetry. So the lowest energy state here, all the sites are oscillating the same phase. So it's the bonding of the bonding states, if you want, and this is anti-bonding of the bonding states. So you have plus, plus, minus, minus, plus, plus, minus, minus. And if you go into the upper band, then the states carry the anti-bonding symmetry. So you have plus, minus, and here it's the bonding state of the anti-bonding. So plus, minus, minus, plus, plus, minus, minus, plus. And here is the fully anti-bonding configuration where you have plus, minus, plus, minus, plus, minus. Okay. So we do first a measurement of the band structure, both in real space and in K-space, and we find this gapped band structure that I was mentioning. We have two bands here with a gap in the middle. Okay. And what we are going to do is a nonlinear experiment where we focus two laser beams on the two sides of only one dimer in the bulk of this chain with an energy which is set to the middle of the gap. Okay, so we have a pump in the middle of the gap, from two pumps in the middle of the gap. They are focused on two sides of a given dimer, and they are dephased here by pi. So as we crank up the power, locally, we are going to be able to shift the energies of these states. So the one bonding state of this dimer is going to come out of the bands. The anti-bonding is going to come out of the anti-bonding band like this. And at some point, we are going to reach the situation that I was mentioning earlier, where the bonding state here reaches the resonance with the laser, and we have this phase frustration thing. And this is the kind of nonlinear steady state that we measure in this configuration when really the site reaches the resonance with the laser. This is an intensity profile versus position. And what we observe here in log scale is that the nonlinear steady state is really, really peaked on one side only of the lattice. So due to this phase frustration, actually, there is a symmetry breaking that occurs, and only one side stays on, while the other side extinguishes in light, goes back to zero. We can look also at the tails of this distribution, and we see that it's highly localized on one sublattice, and this is related to the chiral symmetry of the lattice. Yes? Yes, indeed. No. It's probably the cartoon here is not exactly. They are not exactly positioned on the right sides, but one of the side here has this population here, which is normalized to 1, and the next side has this population here. So it's like exactly, yeah. So that's the kind of state that we have, and this actually has a name. It's called a gap soliton, because you excite in the gap, you shift non-linearly the site to a given energy, and then it doesn't move. Okay. I'm almost finished there. So basically, what happens is that due to this non-linearity, we are able to shift one side away in energy from the rest of the lattice, and we end up actually with two remaining lattices, we have kind of optically cut the lattice in two halves. One lattice here with terminated by the dimer, but one other lattice here which is terminated by a single site. Okay, so it is completely cut in half. We have kind of introduced, if you want, a nonlinear vacancy in the system, and one good way to visualize it actually is to calculate, this is not experimental yet, but we would like to do it experimentally in the near future, to calculate the Bogoliubov excitation spectrum under the nonlinear steady state that we have created. And if you look at the Bogoliubov spectrum of this chain, what you see is that far from the nonlinear equilibrium, you recover the spectrum of the SSH lattice here. But when you are close to this nonlinear excitation, you have indeed introduced a hole in the dispersion. There is a complete hole in the dispersion. This is a state that has been shifted away from the energy bands, and we see emerging here in the middle of the gap an interface state that is localized here on this small pillar because it's just left alone here on the side. Okay. Okay, so small conclusion. What about Polariton quantum matter? I mentioned originally that if you take a lattice of coupled cavities with nonlinearity, you can realize synthetic quantum materials. So in fact, our system here is very well described by the following master equation, where you have on-site energies, interaction, coupling between sites. It's a driven dissipative Bose-Hugbart model, typically, because it's driven here by the laser, and there are the loss terms which inherent to the cavity loss, well described by this kind of setup. So far, we are working in the mean field regime, okay, Gross-Pitayevsky equation, and one of the current technological challenges is to reach the quantum regime where the interaction becomes strong enough to generate quantum correlation inside the system. So there is a lot of research at the moment to try to improve this U, okay, the strength of the interaction in the system by using dipolar excitons, Rydberg excitons, for instance, so different type of excitations that are more strongly nonlinear. And the long-term vision will be to use this kind of lattices with strong interaction to be able to realize quantum correlated states of light. Okay, but this is for the future. And in the meantime, I thank you for your attention.